a problem that I've modified slightly. Here, well, I'll let you read it, but basically what I've done is I've changed it to provide an acceleration of 2. And the question, however, is to determine the tension in the rope rather than the motion of the cylinder. So the question is, do I need a free body diagram? What kind of problem is this? It is not a time spanner, because what's happening is I'm given this figure and it says, this is what's happening, and at this moment determine something. So it's not a time spanner, so I'm not going to integrate anything. Because it's asking for a tension, that's pretty much a dead giveaway that I'm going to need a free body diagram. So it's going to end up being a chapter 13 type of problem. I begin it by counting the degree of freedom. I think it's fairly clear that there's 1 degree of freedom. If you stop the motor, then nothing can move, and so it's 1 degree of freedom. So what I'm going to do is, since I'm given this motion, well, actually the way I would start is I'd say, well, I need a free body diagram. There's only 1 mass in the system, so I'm going to draw a free body diagram of the thing that's in the blue circle. When I do, I get the free body diagram that is over here, right over here. So this is the free body diagram. I have the mass times gravity pulling down, and I have 3 tensions pulling up. So what I do is I then choose the direction to some forces. That makes it easy. In this particular case, S is measured from the ground to body C, and so I'm going to use S as the acceleration. If you just take 2 derivatives of the position S, you'll get S double dot, and that is the acceleration. When S is positive, the mass is going up, so I'm going to choose up to be positive. So when I do, I sum forces. I have 3 times the tension. I have negative, because it's pointed down, the mass times gravity, and that equals mass of the cylinder, C, times S double dot. If I count the number of unknowns, I see 2, I see an S double dot, and I see the tension. So I'd say, well, I only have 1 equation, but I have 2 unknowns. I need something else. Well, because it's 1 degree of freedom, and because I'm given 1 double dot term, I can find all double dot terms. So I know that it's possible to somehow find S double dot. So I'm going to seek a way of doing that. So I come back over here and I'm looking for S double dot in terms of the double dot terms that were specified. So the only way I know to do it right now is to write the length of the rope. So that's what I'm going to do. I have 1 rope that goes like this. It comes down, wraps around, again, wraps around, and ends right there. So I've got really that 1 rope. These other ropes are constant. So see this rope here, that's a constant. I'm not going to worry about it. This rope down here, that's a constant. I'm not going to worry about it. The rope right in the middle, right here, that's a constant length. I'm not going to worry about him either. When I get confused, this problem originally confused me, and when I get confused, I look around to see what is changing, and then I put a variable on it. Okay. So for example, what I would do is I came in here and I started pulling, or pretended to pull on each of these pulleys. So I'm going to grab a hold of this pulley, not the rope. I'm just going to grab the pulley and I'm going to kind of tug on it and see if I can move it. Can I move that pulley? No, I can't. Because why? Because it's tied down with this rope right there. So that pulley doesn't move. So if you notice, I don't label a variable on that, because it's going to be, whatever he is, whatever his position is, it's a constant, and I don't worry about constants. Okay, the other things, all right, here is a pulley, so I'm going to grab a hold of it with my hand. I'm going to pretend like I do, and I'm going to see if I can pull down. Can I pull this? Yeah, I think I can, because if I pull this pulley downward, then this rope over here gets a little bigger. This rope here gets a little bigger. The extra rope that I need is going to come from over here, and that is going to come from basically here. So all of that rope's just going to slide on by. So yeah, I think I can pull this. I think I can pull this pulley right here. I think I can do that. So what I do is I label a variable. I say, okay, well, let me make a note of that. I'm going to label a distance from the ground down to that pulley. So this would be the absolute. It's not a relative, but this would be an absolute. When I take derivatives, that would be the absolute position, velocity, and acceleration of that pulley. Yeah. Okay. The other thing I'm going to do is say, all right, well, is there any other pulleys I can pull? Well, yeah. How about this one right here? Well, yeah, but if you notice, it's attached to the one above it through a constant. Okay, well, I don't worry about constants. So if I need this mass's or this pulley's position, I'm just going to use the one above him plus a constant. Right? And again, I'm not going to worry about constants. So I still have the same variable. Then I say, oh, well, can I pull body C? Does it move? And so, grab it with your hand and pretend like you pull. Oh, yeah, sure, of course, I can pull this thing up and down. All right. Well, then what I did was I said, well, then I need a variable Z to keep track of that. Right? So I defined that variable Z. I could have used S, but since I'm using ropes, I like my variables up here by the rope. I think it's easier to see the ropes when you label the distances. Okay, well, here's a slight mistake that I also made. I went over here and I looked at this pulley over here, right there. I looked at that pulley and I said, well, can I pull that? And I said, oh yeah, of course, that thing will move as well. So what I did was I came in and I defined a variable x. Now here's the mistake. If you notice, x is the same thing as z with a constant. So z and x are simply the same thing plus this little constant that's there. I didn't see that when I did the problem. Now I'm going to show you what happens. Okay, so what I'm going to do is I'm going to write the length of the rope. So the length of the rope is equal to, and now I've got, let's see, I've got a distance here, that length of rope, that's equal to y, well, minus a little bit up here, a constant, right? So it's basically y. The length of this rope right here, this piece, is basically y. See, what I do is I look at one end of it, it's attached to this pulley right here. The other end is attached right here. So it's basically the difference between these two. Well, this one down here, the position of that is y. Position here is a constant, so it's another y. Now I'm looking for this piece right here. That piece is attached to this pulley, and it's attached to this pulley. So I need the position of this one, that's x, and the position and minus the position of this one, which is a constant. So it's basically x, and like I said, I don't worry about constants. So that's x. Then I need this little piece of rope right in here. Okay, and that is equal to, it's attached to this pulley. So its position is x, and it's attached to this pulley, which is essentially the same as this one through a constant. So it's x minus y right there. Okay, and then the next one is here, which is attached one edge end right there, one end right there. And what I did was I said, I should have said, taking this into account over here, but it's obvious to me that what this edge here, that's z. This edge here, that's basically y, right? Because they're constant apart. So that was z minus y. Okay, so that's what I had there. And now when I add them up, what I noticed is that I have a y here, 1, 2, minus 1, minus another 1. So all the y's disappeared. Okay? So what I'm left with is 1x, 2x's, and I take a derivative of that, and I'm left with 1z. So I take a derivative of that one as well. Okay. Now, I'll take a second derivative because I'm looking for accelerations. So let me take a second derivative. That's real simple. You just bing, bing, bing. Right? And now, according to the problem, the acceleration of the cable was being pulled in at 2 meters per second squared. Right? So it's being pulled in. So L double dot is 2, and it's negative because it's getting smaller. So that's why I put a 2 in for that guy right here. So I put in a minus 2. And then these are double dots. Bang, bang. Okay. Now, if you look at that equation, that's when I realized I had made this mistake of a constant over here, right? Because what I do is I look at that and I go, now wait a minute. It's supposed to be 1 degree of freedom. That means I should be able to find x double dot. Or if I want to, I could find z double dot. But what? I've got one equation, I've got 2 variables in there, and so I'm scratching my head going, huh? What? I know that can't be. I just know it cannot be because it's 1 degree of freedom. What the heck is going on? So now I have to look back and say, what did I do? What did I do? Well, then now I can't tell you how I recognize this, but then all of a sudden I realized, oh, it's the z is related to the x because they're related to this constant, right? So I wrote that down. Z is equal to x plus a constant. And then you take a couple of derivatives of that, and you end up with the z double dot. And I'm leaving off my dots here, but there we go. So I say, aha, using the z double dot equals x double dot, then I just bring this this equation right here, and I bring it down right there, and I combine it and say, oh, okay, well, x is equal to z. So then I can solve for z double dot, which I do right over here. Z double dot is a negative 2/3. Now, how in the world do I find the s double dot? Well, it's basically the same thing. What I'm going to do is I'm going to walk from the roof to floor. Right? So what I'm going to do is I'm going to walk a distance of, and we'll say down is positive, so I'm going to walk a distance of z. Then I'm going to walk a constant until I get to the bottom of c. And then I'm going to walk a distance of s. And then I'm at the floor. So I'll call that, we'll call it h, the height between the floor and the roof. So we'll take a derivative of that. 2 derivatives. The derivative of constant is 0. So what is s double dot? S double dot is minus z double dot. And that's what it did over here. What I did was I said, oh, it was obvious to me that they were opposite of each other. And so I just wrote it down. But this is how you can prove to yourself if you're kind of unclear. So it's similar that I did before. So you just walk from one edge to the other. Okay, so what do I do? Well, now that I know the s double dot, I put it in over here. So this term right there is the s double dot. And now I have just the one unknown, and so I just solve for this t. So the t will equal mass of c times 2/3 plus mass of c times gravity
divided by 3. And that'll be your tension that's required to make this happen. Next question you might say is, well, I wonder if the rope breaks. And you notice I didn't make any assumptions about that. I would check it just simply by the tension. If the tension is greater than what the rope can hold, then I would conclude that the rope breaks, and then it's 2 degrees of freedom because I'm pulling in on the rope, and the body C is falling. So, all right, so that's